All right, good afternoon. Let's get started with the class. For announcements, homework 8 is posted, so take a look at that. That's due the last day of classes, which is actually tomorrow, December 12th. Be sure to turn in your case for your ITLL components, or actually the ITLL case for the components. That belongs to them, so turn in your case. You can keep all the components yourself. And the final exam will be held Tuesday, December 17th, from 7:30 until 10 p.m. plus 30 minutes grace period to be able to submit your exam. That will be held during the regular university exam period. I will have a Zoom session up. I recommend joining the Zoom session. It's not required, but I recommend joining because if you need any clarification on anything, I will reply on Zoom, and then you're going to submit your exam to Canvas, and I will send out an announcement via Canvas in the next couple days about the exam. So during the previous class, we talked about path loss and propagation modes, and we also started talking about RF performance parameters, and we're going to continue with RF performance parameters. So we started talking about noise figure, and noise figure was a figure of merit to describe how much noise a device adds to the signal in an RF circuit or an RF system. I wanted to talk a little bit about cascading noise figures, or actually noise factors, which can be converted from noise figures. Many times we have a cascade of components, this RF chain, with many RF components, and a signal might get amplified, might get filtered, might get mixed throughout the signal path. So each one of these components has a gain. So I have the separate gains listed here, and also each component has a noise figure. And oftentimes we want to take all of these components and combine them or cascade them into one noise figure or one noise factor. When I write F, that means noise factor. When I write NF, that means noise figure in dB. I often use those terms interchangeably, so I'll try to be more precise. But the noise factor here, if you cascade these all into one combined noise factor, is this. It's the sum of the first component. Let's say the signal is going from left to right through this chain. The cascaded noise factor would be the first component's noise factor plus the second component's noise factor minus 1 divided by G1 plus the third component's noise factor minus 1 over G1, G2 plus dot, dot, dot. You can see the pattern here. Okay, so this equation is derived if you look back at the definition of noise factor and you actually combine noise temperatures and see what happens to the noise temperatures with the gains as you go through this system. Okay, so something to notice here is that a gain greater than 1 reduces the noise contribution of the next component. For example, so F2, the second component, well, there's a minus 1 in there, but its contribution is divided by G1. So if the first gain is big, then that significantly reduces its contribution, that second component's contribution of noise. Okay. A high gain amplifier is often used as the first component to set the noise figure for the system, or approximately set the noise figure of the system. If that first component has a very high gain compared to the losses of the rest of the system, then that first component's gain, or that first component's noise figure, can actually approximately set the noise figure of the whole system. And this is why we use a low noise amplifier near a receive antenna before the rest of the components in a receiver, so that we can keep that noise low with a large gain relatively for the LNA. When talking about noise figure, there are a few values to note. So a noiseless device has a noise factor of 0 dB. You can't achieve that, but that's as low as you could possibly go. A typical LNA might have a few tenths of a dB noise figure, and usually less than about 3 dB noise figure. And they usually have a gain of around 10, maybe 8 to 15 dB, sometimes a little higher. An attenuator's noise figure is equal to the loss. So if you have a 6 dB attenuator, it's reducing the signal by 6 dB, then the noise figure will be 6 dB. Okay. Let's continue on with RF performance parameters. Let's talk about 1 dB compression point, often abbreviated P1 dB. So an amplifier's gain is constant for low power, but that gain compresses or gets reduced for higher power inputs, which would cause higher power outputs. Okay, let's talk about what I mean by this. Oh, so let's see here. I hear someone's audio, so I am going to mute everybody. Feel free to unmute if you want to ask a question. So let's take an example here. Let's look at an example of a 26 gain actual amplifier. Here's the line out of the data sheet that describes the RF parameters. Here's 26 dB. And let's plot output power versus input power for this amplifier. So what you'll notice is ideally, this output versus input power should be a straight line. So if I put in some relatively low input power, minus 16 dBm, I would add 26 dB of gain to that, right? And I would get 10 dBm out, okay? If I increase that input power to minus 6 dBm at the output, add 26 dB to that, I should get 20 dBm. So you have a slope of 1-to-1 for this P out versus P in, ideally. If I increase the input power to plus 4 dBm, you would expect plus 4 dBm plus 26 dB is 30 dBm. Okay, but what you would notice is in reality, if you have this amplifier on the bench connected to test equipment, you would notice that the gain actually trails off here. It actually gets what we call compressed. Okay, and so if you see for this amplifier about 29 dBm, then you're compressed about 1 dB. Okay, and that 1 dB compression point is the output power level at which the gain decreases by 1 dB from its constant value because you're operating at the upper end of the power capability of this amplifier. So here is this 1 dB compression. Ideally, I'd be on the blue line, but I'm actually on the gray dotted line, and I'm 1 dB lower. So that power, that output power at which that compression happens, that 1 dB compression happens, is the 1 dB compression point. Okay, so you see instead of 26 dB gain, you have 25 dB gain. So that means the P1 dB at the output is 29 dBm because that's where the amplifier is compressed by 1 dB. And that's what's listed here in the sheet. So P1 dB or 1 dB compression point roughly describes the maximum output power at which the amplifier can operate approximately linearly. Okay, and when you operate above this 1 dB compression point in that nonlinear gain region, it's not 1-to-1 slope constantly anymore, the signal is going to be distorted. And that produces undesired signals. So when you start approaching or go beyond that 1 dB compression point, you're going to see some undesired signals, including harmonics. That means you're going to have integer multiples of the fundamental frequency that you put in. So if you put in 10 megahertz into the amplifier, you might get 20, 30, 40, 50 megahertz multiples at the output because of that nonlinear characteristic. You might also see intermodulation products. So intermodulation products will increase near the compression point. And these are sums and differences of integer multiples of frequencies. And that's just like frequency mixing. In a mixer, we wanted this nonlinear characteristic so that we could cause these intermodulation products, right? Normally undesired, except when you're using a mixer. But in this case, if we're just using an amplifier, and we don't want these products, well, that's undesired. So for higher power efficiency, there's an exception. So if you are transmitting or working with a waveform that where you don't care if the amplitude is distorted, some amplifiers actually are operated in compression for these signals, where you're not representing information with the amplitude. You might be using frequency or phase, and for some pulse amplifiers. And usually you'd follow those amplifiers by filters to remove any undesired products in frequency. But some amplifiers, in order to get higher efficiency, are operated in compression or past this 1 dB compression point. All right, let's take a look at a cascade analysis. So I'm going to show you what happens when you cascade or combine components together. Okay, let's do this by example. Let's say you have a signal from an antenna at 145 megahertz, and it's received at the antenna port at minus 115 dBm, and that signal occupies a 5 kilohertz bandwidth. And then you have a down converter that shifts the signal from the RF frequency 145 down to 10 megahertz for demodulation. So we have an amplifier, there's an attenuator, there's a filter, sorry, there's a filter, there's a mixer, there's another filter, and another amplifier. And so gain and noise figure and losses are shown here. So the question is, what is the signal power and signal to noise ratio at the down converter output? That's what we care about, right? We care about being able to demodulate the signal when it's down at the intermediate frequency. Okay, so let's represent the cascade of components for the purpose of this analysis as a single noiseless amplifier with noise inputs. Okay, so we're going to convert each noise figure to a temperature. We saw that conversion when we talked about noise figure. And then we're going to refer each component noise temperature to the input of the model. And this is the model. So we want to take this whole circuit and replace it with this equivalent. So we have some input noise from the antenna that comes from the outside world. Let's say it's an antenna, it's sitting there at room temperature. It's going to have thermal noise input, and then we have some equivalent noise temperature in to get a system noise temperature that's the sum of the two, and then a noiseless amplifier. We're going to use that to calculate, okay, what is the signal output, what is the noise output, and figure out the SNR. So let's create a table here. Here's the Cascade Analysis spreadsheet table that I created for the circuit. Here are all the components. Here are those components' gain and noise figure values. Remember that if you have a loss or an attenuator, it's generally a loss, that the noise figure is equal to the loss. So negative 3 dB gain is a 3 dB loss. That's a 3 dB noise figure. Okay, I have cumulative gain. So if you just add these gains up as you go along, this is a cumulative gain, right? And then I calculated the output power in dBm for the signal, the noise temperature, and then calculated the noise contribution of each component to the equivalent model here, right, to the system. So the signal output is minus 115 dBm. That's what's at the antenna here. Plus 35 dB, that is the cumulative gain of all of these components. So I'm going to have negative 80 dBm at the output of the circuit, right, and at the output of this equivalent here. If I sum up all the noise contributions at the input, right, just refer these back to the input, back them through the gains and go back to the input, then I get these noise contributions of each component. You can see how the first amplifier contributes the most noise, and then because of its relatively high gain, 22 dB, you have smaller contributions later by these other components, right? Especially compared to the first amplifier's contribution. The system noise temperature in the into the noiseless amp is therefore TE plus TN, right? These two sum together, we have TE here. That's 381.6 Kelvin noise temperature. And the noise power into the amplifier is then KTB. Remember Boltzmann's constant times the noise temperature times the bandwidth. So you get converted to dBm minus 135.8 dBm. Okay. Now that's into this amplifier equivalently, and then out of the amplifier, just add the gain, add 35 to that. You get minus 100.8 dBm at the output of that amplifier. Okay, so we've referred all of those noises back to an equivalent noise temperature. We multiplied it by the cumulative gain, and at the output, we're going to see this signal of minus 100.8 dBm here in the noise model, and also here in the real circuit. That's how big the signal is going to be. Oh, I'm sorry, that's how big the noise power is going to be. Calculating noise here. And then the SNR would be S divided by N, or in dB units, S dBm minus N dBm minus 80 minus a negative 100.8. So we get a 20.8 dB signal to noise ratio. And then we can calculate the noise figure of the cascade by doing this. Use the noise temperature that we calculated, the equivalent noise temperature, and convert that into the noise figure. Okay, so this whole circuit has a gain of, where was it, 35 dB. If we have a minus 115 dBm signal at the input, we're going to have a minus 80 dBm signal at the output. And we're going to have minus 100.8 dBm of noise. That's the SNR, that's the difference. And the equivalent noise figure of the whole system is 1.2 dB. So that gives you an example of a cascade analysis to take multiple signals, not multiple signals, multiple components, combine them into a model, cascade them together to get the equivalent gain, equivalent noise figure, and then you can take a signal at the input and figure out what the SNR is at the output. Okay, so this is done a lot in RF systems engineering. So I wanted to show you that. Now I mentioned the amplifier location impacts signal to noise ratio. This is the circuit that we just looked at with the low noise amplifier right at the beginning. And this is the spreadsheet we just looked at. Those are the numbers we just talked about. Imagine you change the amplifier location. You say, well, I'll get the same gain, so I'm going to put the amplifier at the end here for some reason. Okay. And so what you're going to see is the same cumulative gain. Right? We still have 35 dB, but look at these noise contributions. Look at the difference. Because you have that amplifier at the end and not at the beginning, you get these higher noise contributions. Right? So that affects noise performance. So in this case, the noise figure of the system is 10 dB instead of 1.2 dB, and the SNR, it would be 12 dB instead of 20 dB for that case we talked about. So amplifiers near the input of the RF chain reduce the noise contribution of the following components, but they can also cause distortion, as we will see. Now, this is the reason if you have DirecTV or some other satellite service out at the antenna before that long cable that comes down to the satellite receiver in your house, at the antenna, there's a low noise amplifier to put it right up there, right up front before all of the cable loss. So you want that amplifier way up front, and actually there's power on that coax usually going up to the antenna, so that LNA, that low noise amplifier, can be powered up there to put the gain right at the antenna before the loss of the cable, and that improves the noise figure of the whole system. Another metric is third order intercept point, and that describes the linearity of a component. If you have an ideal amplifier, V out is equal to some voltage gain times V in. I'm breaking my rule about power gain, right? I'm talking about voltage gain here. but this helps me explain IP3, third order intercept point. What this means is if you plot V out versus V in, right, you would have a straight line with a slope of A1, right? V out is A1 times V in. In a real amplifier, well, they don't have linear characteristics. They're not perfect. They're close, but they're not perfect. So if you were to have a characteristic that looks something like this red line, you could mathematically express that or algebraically express that using this. V out is A1 V in, right? That's the desired output. But then you have all of these other components, A2 times V in squared, A3 times V in to the third, and so on. And those are multiplications of a sinusoid times a sinusoid when the input is a sinusoid. And that creates signals at other frequencies. These are the undesired mixing products in this case, if this is an amplifier. One of these components is special. It's the third order term because that causes the strongest in-band, close-in frequency, undesired frequency component. Okay, that's the strongest intermodulation product that we would see. We can look at this. Here's a two-tone case. Here's power versus frequency, and I put two tones into an amplifier at power P1. Both of these tones, right? These are tones. They're constant frequency, just sinusoids at FA and FB, frequency A, frequency B, and they're both at the same power level. This will cause signal components because of the third order modulation, the intermodulation at these two frequencies, at 2FA minus FB and 2FB minus FA. Right, so you'll see these poke up out of the spectrum on a spectrum analyzer, or you can analyze it and see this happen. And because they're so close in to the desired signals, they could cause interference with the desired signals. Maybe they're so close you can't filter them out effectively. Okay, so if you look at the two-tone input case, P1 out versus P1 in. So I'm going to look at the input of that first order component versus the power input of the first order component. You get a plot like we looked at before. You get this one-to-one slope, right? We talked about this. This is just the gain of an amplifier. P out is some number times P in. Gives you a slope like this. And it'll be well, actually, it'll be one-to-one. So if you increase P1, if this is in dB value, as you increase 1 dB in the input, you'll increase 1 dB for the output. The third order products act a little differently, right? Because of that V to the third term. The slope is actually 3-to-1. So that third order product, as the input power gets stronger, creeps up higher and higher, faster and faster than the first order product. Okay, at the point where these cross, right, one has a slope of 1, one has a slope of 3, so they can cross at some point. That's called the third order intercept point. That's what IP3 is. The output third order intercept point is this power level right here. And, you know, if you were to actually connect test equipment, test with two tones with an amplifier and measure this, what you're going to see is the signals trail off. The powers don't follow that ideal linear slope here. Okay, so this third order intercept point is actually theoretical. And so the difference between P1 and P3 is 2 dB output power per 1 dB of input power. That's how much closer these are getting, these two lines, red and green. That's how much closer they're getting for every dB you increase in input power. For every dB you increase, they get closer by 2 dB. Okay, so a higher output IP3 generally means better linearity. So an amplifier with a higher specified output IP3 is more linear. You'll have fewer problems with intermodulation products. And there are other products. They're fifth and seventh and ninth on up. They're typically the odd order are dominant here. They also exist. They're at lower power. They still may be problems, but if you have a problem with the fifth, you're definitely going to have a problem with the third. So that's how RF engineers describe typically how linear an amplifier is. It's a figure of merit for amplifiers and other components, describing how linear they are. So let me give you an example of gain and output IP3 measurement. Let's take an amplifier. I actually took this amplifier, connected it to test equipment, and measured with a spectrum analyzer. So here's the measured input. This is power versus frequency. And you can see a spectrum analyzer noise floor in this case here. That's what the flat yellow line is here. But here are the two signals. And they're at 144.95 and 145.05 megahertz, right next to each other there. Each tone is at minus 21.9 dBm. Okay, if I put that into this amplifier and I look at the output on a spectrum analyzer, I see this. You see the original two signals that are larger, so those are the fundamentals, they're larger. But then I see these other intermodulation products. Here's the third order product. Here's the fifth order product. Here's the seventh order product. So they do show up. Okay. And I'm actually not, I'm not too close. I'm not very close to this 18.6 dBm, 1 dB compression point. I'm actually backed off from compression, but you still see these intermodulation products. Okay. So to determine the gain, you look at that, the fundamental, the increase in the fundamental power. So 8.4 dBm at the output minus negative 21.9 dBm at the input, I have 30.3 dB of gain. To determine the output IP3, I do this. The difference between P1 and P3 at 8.4 dBm is this. So I get 24.7. And the difference changes by 2 dB output for each change of 1 dB input. We saw that 2-to-1 closing ratio. The difference shrinks by 2 dB for every 1 dB you increase in input power. Okay, so the output IP3 is this, 8.4 plus 24.7, which is this number, divided by 2, and that's 20.8. Okay. So this becomes important when you're doing testing to look at the spectrum. Don't just assume when you're working with RF signals, especially at the higher end of the power capability of a device. Don't expect the spectrum to be clean at the output. Here's a nice clean input, but at the output, you'll see intermodulation products at frequencies you may care about. You may not want those signals there. Okay. All right, let's take a look at link budgets. So, we started this conversation about RF saying we really care about communications range and communications quality, and that's where link budgets come into play. Let's talk about an RF link budget. So this is what it is. An RF link budget accounts for transmit power, it accounts for antenna gains and propagation losses from a transmitter to a receiver. So I have an information source, transmitter outputting PT transmit power into an antenna that has GT gain. I have path loss, LP. I have a receiver antenna with gain GR, and I receive power PR here, and I care about that received power and its signal to noise ratio. So link budgets are often calculated to determine the range of a system, the distance between transmitter and receiver that gives an acceptable quality for a given system. Or if you're given a distance, you want to calculate the quality, you want to estimate the quality for a given system. So that's what link budgets are used for. Or if you want to establish the requirements for a system to be designed for a given quality and a given distance. Okay, so we have path loss, which includes free space path loss. We talked about that. But also, if you're transmitting on the ground in a city, you have path loss due to attenuation by buildings, trees, the atmosphere at certain frequencies. So we have to take that into account in the received power calculation. Right, so we talked about received power being PT plus GT minus the path loss, but there are some other terms in here that we have to account for, right? So in that path loss, we want to account for attenuation by objects. And also with another loss term, we want to account for cables and connectors and external filters and other components that may be between the antenna and the receiver. We also probably want to include a loss margin. And that accounts for unexpected component performance. If a component's a little higher on gain, lower on gain, a little more loss, a little less loss in a filter, we can account for antenna polarization mismatch when you don't have antennas, their polarization aligned with the electric field that you're receiving. And also fading due to multipath, which is something you've probably experienced if you ever listen to FM radio. Okay, so let's talk about this. I want to get a little bit into multipath fading because, again, I think you've experienced this. If you have a transmitter and a receiver, this could be an FM transmitter, you're listening to the radio in your car, and this is your radio receiver. You may or likely have, if the transmitter antenna is up on top of a mountain, you might have a line of sight path. That's the primary path of propagation between the transmitter and the receiver. Or you may not if that path is blocked. But if you're in a cluttered environment with reflectors and scatterers, then you could have a multipath component. A multipath component is a signal that propagates from the transmitter, reflects, refracts, gets scattered by an object in the environment, a physical object, and makes its way back to the receiver. Okay, you can have multiple multipath component. And each one of these has a different time delay, right? RF energy in air propagates at the speed of light. And so these all have different delays. So each multipath signal arrives at the receiver with a different phase depending on each path length, right? The phase and delay are related, as we talked about. And multipath signals at the receiver they add together. Those fields add where the antenna is located, and you can get constructive and destructive interference, right? The multipath signals and the line of sight might add in phase, you get a bigger signal, or if they add out of phase, then you can get a smaller signal because of that combination of sinusoids out of phase. So that multipath caused power, that power in the presence of multipath, depends on the position of the receiver in space and the strengths and phases of the multipath components and the line of sight component. And so you can imagine you're at one place, you get one strength, you move the receiver a little bit, maybe a quarter wavelength away, you get another strength, another power out of the antenna, move it a few feet another way, you get another power, and that results in changing power levels as the receiver moves. Right? So as the receiver moves, the received power rises and falls with time or with distance. If it's really with distance, but if you're moving, it's with time as well. And that results in a fading signal. So even though you have a constant signal, constant amplitude transmitted, as you move, you're going to see a a fading signal. And so for RF systems operating in a multipath environment, our link budgets often include a margin to account for this fading. So I think you've experienced this. Many of us have. If you're listening to an FM station that's kind of, it's sort of weak, and then you stop at a stoplight and it's fine, you move up a couple feet and the signal, you just hear the interference, you hear what we call static, right? You hear that noise, and then you move forward a few feet and then, oh, it's fine again. Well, that is this. You're experiencing multipath fading. And in this case, where you see this kind of fading, where I have a particular case, a line of sight plus two multipath components that are 16 dB and 18 dB respectively below the line of sight, you might include a margin of 3 to 4 dB, right? Because you look at the fade, you might analyze this, figure out what the deepest fade is. I see a 3 dB fade almost. Maybe I'll put a 4 dB margin in on there so that when I'm at this position in space, I don't get a loss of signal. Eventually, you can get so far away, the signal level gets so far down that you'll experience fades. But let's say you're designing for a certain distance, away from the transmitter with certain multipath parameters. In this case, you might include this kind of margin. So here's an example of a link budget. Let's determine the maximum range of an FM communications link. Let's say you have a handheld radio, an HT, handheld transceiver, and you're communicating with a base station. And so the handheld transceiver has what we often call a rubber ducky antenna. They're these flexible antennas that are durable, so you can bend them and they won't break. They don't have particularly high gain. And then you have a monopole antenna trying to cover an omnidirectional pattern, and that's connected to this base station here. And you're propagating over free space. So there's line of sight propagation over free space, but you do have a multipath environment. Let's say this system's operating at 440 megahertz. It's designed for line of sight and multipath components. And the RF signal occupies a 15 kilohertz bandwidth. And you want to specify a quality. So you want an SNR at the receiver to have good voice quality. And let's say that's 20 dB SNR at the receiver. That should give you some good voice quality. And let's include a 4 dB margin for multipath fading, just as we discussed on the previous slide. So here's the steps you would take. You would determine the required received signal power at the receiver to meet the SNR. Let's figure what power we need. And then let's determine the maximum path loss that gives us that received power at the receiver. And then let's determine the range corresponding to that maximum path loss from step 2. So I'm going to use this model where we have the receiver is equivalent to a noiseless amplifier with input noise from the antenna and an equivalent noise temperature, and its output goes to a demodulator, and that's where we want this signal to noise ratio to be 20 dB. So let's start with step 1. Step 1 says the received noise factor is 10 to the power of NF over 10, right? So we have, did I give you a, yeah, over here. The noise figure of that receiver is 2 dB. So its noise factor is 1.585. Its effective noise temperature is this. Noise temperature is 290 times the noise factor minus 1. Right, so that's 169 Kelvin. Right, that relates to the noise power there in this model. So the system noise temperature is Tn plus Te, and that's going to be 290 plus 169, 459.6. So that's right here. That's where that noise temperature is. Remember, you can calculate the noise power at any point when you're using noise temperatures using KTB, right? KTB. If you know the noise bandwidth and you know Boltzmann's constant, you can calculate the noise power. Okay. So let's do that. We have the bandwidth. So let's calculate receiver noise power. Boltzmann's constant times the system noise temperature times 15 kilohertz. I think I set up here. Yep. And so that's minus 130.2 dBm receiver noise power. Right? And so the required received power for the signal is then the noise plus the SNR. And so we need minus 110.2 dBm. That's the power required at the receiver for a 20 dB SNR. Okay, so that's the RF power we need there. Step 2, let's determine the maximum path loss required for receiving that power. So here's that equation. The received power is this, power transmitted plus the gains of the antenna minus the losses. I can rearrange that to solve for the path loss. I just rearrange this equation to find the path loss. I'm working in dB units here, dB, dBm units, so that we can use addition and subtraction instead of multiplication and division. I'm going to convert the transmit power to dBm. Okay, so I have 100 milliwatts transmit power, 1.1 watts power. That's 20 dBm. And then I can calculate now, based on the other numbers that are given in this example, the path loss. And so I have 120.5 dB path loss that is allowed for me to have minus 110.2 dBm at the receiver. Now we're assuming free space path loss. So we can use this equation for path loss, 4 pi d over lambda, quantity squared, convert to dB. So I get this. I plug in my numbers. Right, here's the wavelength. Here's the path loss. And the distance is 57.6 kilometers, or if you're speaking to an American who only knows miles, 35.8 miles. All right, so that's pretty reasonable. You can have a base station with an elevated antenna, maybe on a tower, so you get line of sight propagation. With a simple antenna, a monopole with a sloping radial ground plane here. Mount that up on a tower to give you omnidirectional coverage all around, roughly. And then you could have a handheld transceiver out here with a small antenna and be able to communicate 35.8 miles and have good voice quality at a 20 dB SNR. So that's a typical top level communication system, RF communication system analysis to use a link budget to determine range or figure out what transmit power is needed or figure out the noise figure requirement on a receiver. You work with what you do know, you calculate what you don't know or what you need and specify it. And this is an example of doing that. I'm going to end our discussion of RF communications here. And I'm going to bring up another slide. So we have hit the wall on time almost for the class, and we have hit the wall on time for the course. So I wanted to do a brief course summary in the few minutes we have left. So, kind of a debrief to make sure we hit all the objectives here, and just to refresh your memory a little bit on what we've talked about and what I think you should carry forward as useful topics into your future projects and jobs. So our course objective was to cover electrical engineering topics that span across a wide range of electronic systems and subsystems, and that where these topics impact non-electrical engineering disciplines. And we worked on this project. And I hope that now, staring at this diagram, unlike the first day of class, all of this makes sense, right? You can identify these areas and you have experience in each one of these areas now, right? We talked about circuit theory and analysis. We went back to capacitors, inductors, resistors, and we even applied Ohm's law to figuring out like what wire gauge do you need from a solar panel to a system so that you get reasonable power efficiency and you can spend less on solar panels. And we talked about electrical test and measurement. And for many, this was a review, but I hope it strengthened your knowledge and your abilities in our lab and other labs in order to use typical test equipment. And we talked about power sources and control. Right? We talked about battery packs and battery capacity and different battery chemistries and rechargeable batteries. And we talked about motor drivers and how to use a MOSFET to implement pulse width modulation to drive really any load like a motor. We talked about sensing and controlling with microcontrollers, both the hardware and the software. So you got your hands on and we talked about theory of different microcontroller topics and peripherals and timers and interrupts and things like that so that you could use and understand software. You could write your own software or use template code and figure out how it works and implement it. We talked about electronic sensors, both analog and digital sensors. We used an analog temperature sensor in class, in lab, and you had a digital output from an infrared obstacle detector to measure RPM, right? And we talked about IoT. We talked about MQTT and how to use publish and subscribe architectures in order to send messages through a broker between clients. And we talked about RF communications, right? And how an RF communication system works and what a transmitter and what a receiver does, what the components are, how antennas work at a basic level, how to calculate path loss and do link budgets, okay? And then through lab, we worked on electronics prototyping skills. So I hope that was valuable to give you some hands-on work there in the areas of electronic components, handled the electrical aspects, but also the mechanical hardware and mechanical interfaces, right? You had to solder. You had to make sure your wires didn't break. You had to have some strain relief in there. You had to make sure your project was rugged enough. So I hope there was some interface and overlap between the electrical world and the mechanical world in lab. And then we got you into doing software and processing signals from sensors, right? And then we rolled that up all into one project that had a closed loop system and wireless communications. Okay, so I think we achieved the objectives. I'd love your feedback. If the FCQs are still open, please submit one. Or if you just want to send me an email or note anonymously or otherwise, I'd love to hear your feedback. But we will close the class now. Don't forget, homework 8 is posted. Turn in your component case to the ITLL. Final exam will be on Tuesday. I'll send out an announcement about that. And thank you for taking the class. I really do appreciate this. I know this is special topics and elective, and I'm really glad to have your interest in this class, and I'm glad you took it, and I hope you got a lot out of it. So I will start office hours in just a few seconds. So if you'd like to join, please join. If not, I'll see you next semester. Have a great night. Have a great break.